Log on, tune in, find out. Another good idea from Cambridge.
And he will speak on Quiver varieties and tensor products.
Thank you very much for the introduction. So I'd like to thank organizers for invitation. And I also want to dedicate this talk to victims of the earthquake of East Japan, which happened just 1 month ago. And I think the number of Japanese speakers show that still academic life in Japan is very active and unchanged. And I hope ordinary life in Japan also recover very soon. Anyway, I talk about Quiver varieties and tensor product. It's only related with derived categories, so it's slightly different from the theme of this workshop. But anyway, so I talk about. So let G be a real algebra of type ADE. Then so you can consider, you can define the so-called quantum affine algebra. Or the so-called Yangian. So these algebras are defined by generator relations, which I will not recall. But I just say that this Yangian quantum affine algebra is usually used by UQ Jihat. So quantum affine algebra is a deformation of the universal enveloping algebra of the affine algebra, which is the central extension of Laurent power series of the finite method algebra. And the Yangian is some kind of degenerate version of this quantum affine algebra, which is deformation of the loop enveloping algebra of the current algebra, C of G, so which is just polynomials in G. So today, by some technical reason, I mainly talked about Yangian. And so in some years ago, I constructed a representation of quantum affine algebra using the so-called Quiver variety. And also there's some version which you can construct representation of Yangian. And but so there's this object. These two algebras are studied by algebraic way, and one of the key structure of these algebras are the co-multiplication. So these algebras are Hopf algebra, and you have co-multiplication. So which usually denoted by delta. So I write A for the algebra for both, for either Yangian or quantum affine algebra. So since this is a co-multiplication, it maps from A to a tensor A. And this co-multiplication is not co-commutative. But it's almost co-commutative, and but almost in some sense. So you have some R matrix, the so-called R matrix, which intertwines the representation of V tensor W and W tensor Z. So in fact, in this quantum affine algebra setting or Yangian setting, so this R matrix depends on the parameter, which is usually called the spectral parameter. So it's written usually by RU. So U is called spectral parameter. Well, later I will talk about more general case, but at the beginning I'm talking about the finite dimensional representation of those. And this R matrix satisfied the so-called Yang-Baxter equation. So in fact, this is spectral parameter. So it's like so R12, R13, R23 is equal to. So this the relation of the braid relation, and so this structure is ultimately related to the knot theory and such and similar some. Related to knot theory. So my problem which I want to discuss today is describe these structures so namely this co-multiplication R matrix and similar structures via geometry. Quiver varieties. So this is the problem which I want to consider. And why this problem is interesting? And first, it's clear that since these structures are important and intensively studied by those algebraic approach, so we should also have some geometric approach to this problem. But also another more, I think the reason why this problem is important is so this construction of the representation of quantum-affine algebra or Yangian has a similar flavor with what we just had the last talk. So you define so as I said, this is defined by generatand relation, and we want to we define the generator as a correspondence and check the defining relation. But this is somehow I think the stupid approach, because I mean a priori there's no reason why this relation to be held, and just we checked, and we don't have any philosophical or how to say conceptual explanation of why such relation holds. So we want to have more conceptual understanding of this UQ G hat or Yangian symmetry on Quiver varieties. So to this question, this R matrix or co-multiplication is useful because originally those algebras are found starting from this R matrix. So original definition or introduction of this quantum, this UQ G hat or Yang is coming from R matrix. So this is so-called RTT realization. So instead of starting giving generator and giving relation, you start with some vector space and R matrix, and then there's some way to construct UQG hat or Yang from those data. So which I will not go into detail today, but if you look at the standard textbook in quantum groups, you can find such. For example, in the Cassell's quantum groups, you can. And this, as I said, this is the original definition of, and these are matrices coming from integrable system. And so this is somehow, I think, the most basic realization of the quantum group. So in this way, I really want to understand these structures. And also, there's some another reason why such understanding is useful. Another. So in the algebraic approach, so as I wrote, G, we must assume G to be finite dimensional real algebra. ADO army. So you can write, you can you can have some twisting that so to deal with F type F and G. But anyway, so in the other these construction, this co-multiplication and R matrix can be studied only when G is finite dimensional, and there's some technical or fundamental difficulties to generalize this co-multiplication of R matrix for more general G. But for Quiver variety can be defined for arbitrary symmetrizable Katsumudi real algebra. So G arbitrary. And in fact, as you heard in the previous talk, so this Quiver variety has origin with this Mackay Quiver, and the most natural Quiver is of affine type. So this is most closely related to geometry. So in this case, the Yang or UQ of G hat or Yang is called the toroidal algebra. So again, these are given by generator and relations, and so this is an algebra. These are algebra, but so far we don't know how to construct those co-multiplication of R matrix in the algebraic approach. So if you can understand this structure by geometry, then you have some chance to generalize these objects in these affine setting, which I think is interesting. And this answer to this problem was known for some years ago, 10 years ago, by Baragnolo, Barcelo, and myself. But the answer is, so we don't have a satisfactory answer to these are only partial answer. So we have some hint how these structures are defined, are understood by geometry, but not completely satisfactory. But so recently, so today, some more satisfactory answer based on some recent work by W. Morik and Andrei Okounkov, which is still in work in progress. So in my old previous approach, we partially use algebraic structure to explain these. We use both geometry and algebraic structures to understand those co-multiplication and matrix. But this algebraic part in this recent approach, they make everything in purely geometric way. So, and in particular, it works for arbitrary Kac-Moody, symmetric Kac-Moody algebra. And in particular, because we use both algebraic and geometric structure, so this previous approach works only for G type AD. Okay, this is just what I want to say today. Introduction for what I want to say today, and I will explain some more detail. So first, I will explain Quiver varieties. So Quiver variety can be defined for arbitrary Quiver, but today I want to consider only for affine case, which I think is the most interesting and most closely related to geometry. And also this Quiver variety of affine type includes Hilbert scheme of points on the resolution of simple singularities, which we just had in the previous talk. So again, I fix gamma finite subgroup of SL2. And we have affine real algebra G corresponding affine real algebra. So like in the previous talk, so the Quiver variety is a modular space of some sheaves on the quotient, but I use a slightly different framework. So I consider the modular space of framed torsion free sheaves gamma equivalent, gamma equivariant torsion free sheets on P2, which is the compactification of C2 together with line at infinity. So here framing means that so this is the sheaf, torsion free sheaves, gamma equivalent torsion free sheaves on P2, and framing is just the trivialization of E restricted to line at infinity and trivial vector bundle at line at infinity. But since these are gamma equivalent, so I can twist this by some by gamma module. Then these modular space. So I first fix W, and I consider the modular space. And this modular space is parameterized by discrete data, which is some kind of like a second Chern class, not a kind of Chern classes, which in fact in this particular case you just consider V, which is the homology of this sheaf twisted by line at infinity. In fact, by this the existence of framing, the H0 and the H2 vanishes, so this is equal to alternating sum of cohomology group, in fact. But anyway, so this is the gamma module. So the modular space, this is a kind of Chern class. The modular space is parameterized by those discrete data. So I denote the modulus by MVW. So V and W is an isomorphism class of gamma modulus. So if you take W to be the trivial irreducible representation, then this is not exactly the same as the Hilbert scheme of points on the resolution, but it's very close. And then V is just again trivial representation, like some M. Then this is like X. No, this is regular representation. Sorry.
Rank 1.
This is a trivial, so this is automatically rank 1, I think. Trivial and irreducible.
Gamma is the orbital with the resolution, or what is it?
Well, so X gamma was the given in the previous talk. This is the resolution.
The resolution.
Yeah, but in this definition, in fact, it's not really isomorphic to this, but it's just birational. So
It probably is to the Hilbert scale of points on the orbital, given on the nodes.
well, so this is just how you call this the modular space of frame sheaves. If you call this as Hilbert scheme, then it's so. But otherwise, so this is a thing. Well, but anyway, yeah. Let me see. It's really important to see this coalgebra structure. To see this coalgebra, you really need to consider more general W. So otherwise, you can't see. So I denote MW as just the total disjoint union of all VW. I fix V W and move all these. And I also need the so-called Uhlenbeck space, which I usually denote by M0 of VW. So this is, in this special case, it's like a symmetric product of this singular overall. Well, I don't think I really need some detail of the definition of this space, but by construction, you have a projective morphism from MVW to M0 of VW, like Hilbert-Chow morphism. So this is a projective morphism. And if you impose some conditions, then this is a resolution of singularities. So in many cases, this is a resolution of singularities. So I forget to say this. This is non-singular, and this M0 is singular. Affine algebraic variety. And again, like in this case, I need to consider the union of all those M0 VW. And in this case, in fact, I need to explain how M0 different V for M0 for different V relate to each other, but it's a little bit technical, so I don't want to go to anyway. So you just imagine that in a symmetric product case, SNC2 divided by gamma is embedded in Sn plus 1 C2 divided by gamma if by adding the singularity at the origin, a point at the origin. Adding how to say, origin of C2. So generating this inclusion, you have some relation, inclusion M0 VW into M0 V prime W if V prime is larger than V. So by this inclusion, you consider the inclusion, and then I have a map. So the fundamental thing which I will consider is the variety ZW, which is a fiber product of MW with itself over this M0. M0W. So this is called so-called the analog of Steinberg variety. But I want to emphasize that this is a little bit cheating because I introduced this kind of strange union of MVW and M0W. So like in the case of Hilbert scheme of points, so this is a union of infinite dimension of infinitely many copies of space, and in particular, the dimension is increasing. So this is again Steinberg variety, analog of Steinberg variety, is a union of infinitely many varieties, and in particular, so this is the union of MV double, and but these two copies might be different. And I consider that the fiber product over V plus V prime and V plus V prime. So the fiber product, I may take this may be fiber product of different spaces.
Sorry. So is this guy connected? This, when you take this union over these inclusions, is that this space?
Yeah, well, but this I never use this as a geometric object. That is how to say. This is infinite dimensional space.
Yeah.
So, which I mean, how to say? It's some in this particular case, it's just the limit of symmetric product. Which I mean, of course, you can study it in geometric way, but I always this is a shorthanded notation. I always treat the space as the union of these. And this kind of picture is already implicit in the case of Hilbert scheme. So the operators usually is a fundamental class. Generators are given by the fundamental class of irreducible components of these varieties. And I usually consider the subvariety in any pairs of the number of points. So Hilbert scheme of n points and Hilbert scheme of m points, and n and m may be different. And in fact, so treating different different number of points simultaneous is very, very important to construct this representation. So anyway, this. I think I need a little bit more notation. So G is a group. Script G is the product of general linear group of W commuting with gamma action and C star. This acts on MW and M0W. Because first this acts by changing of the framing, this change of phi, and the C star acts on P2 or C2 by just multiplication, which is commute with the action of gamma. So this GW is and also GW is also a G variety. So in this setting, well, Agnolo construct algebra homomorphism from Yangian to the equivalent homology of this. Steinberg variety, which is not neither injective or surjective in general, but somehow how to say? In some sense, it's close to isomorphism, and in particular, the representation to understand the representation theory of Yangian, it's enough to understand the structure of this.
The Z's are no longer smooth, is that right?
G is no longer smooth. Yeah, G is very singular.
component equidimensional?
Yeah, yeah, it's Lagrangian. I mean, of course, I'm talking about this component. This is Lagrangian. Lagrangian with respect to holomorphic symplectic, natural holomorphic symplectic structure on the variety. So as I said, I repeated what I said in the beginning. So this is a algebra homomorphism, but this is a Hopf algebra. So if G is of type ADE, so I want to understand the co-multiplication in here, and in type ADE, and if one can really do understand it in geometric way, then as I said, you may have some choice, a chance to generalize this construction for arbitrary symmetry, the Katsunori algebra. So I denote this algebra by AW. So this depends on the class W. So W is a isomorphism class of gamma volume. And so this W is this is independent of W. So W is somehow considered W corresponds to highest weight of the G in some sense. So the co-multiplication, if once once co-multiplication is defined, then it should not map AW to the tensor product of AW with itself. If you consider the tensor product of integral finite dimensional representation of real algebra G, then its highest weight is summed up. So the co-multiplication should be mapped in this way. So AW should be mapped to AW1 tensor AW2, so W equal. Since W corresponds to highest weight. So now, as I said, from this, it's really important to move all W, to consider all W simultaneously. So if you fix W, then you can't see this structure. So now. So next, so then somehow, so go back to the geometric description of this algebra. So AW is a homology of ZW, and ZW parameterize those pairs of torsion-free sheaves. So the problem is there's some I mean, what is the relation between MW1, product of MW1 and MW2 and MW? So are there any relation between them? So in fact, there is very natural object connecting the two modular space, which I mean, in fact, appears in many contexts. So which I denote by T of W1. T stands for tensor product, T of W1, W2, which is just given by 0, the short exact sequence. But by some reason, I denote the first time by E2. Then the projection here is just taking this last term and the first term, and this projection is just middle term. So this is a very natural object connecting to such modular spaces. And one important thing, remark that this depends T W1, W2 depends on the order W1, W2. I mean, since this is a short exact sequence, so the first and the last term are completely different. So in particular, this T this variety is not the same, but this is compatible with this R matrix is not a co-commutative, which I think I raised. But as I said, this R matrix is almost R matrix interchange V tensor W and W tensor V. I didn't really say that this. I should not really say. So this depends on the parameter U, which is in fact the variable corresponding to equivalent cohomology. And this R matrix has some pole when you use a special value. So this is very important in the representation theory. And so both two varieties are closely, they are not the same. So that is the reason why this R matrix can't be defined everywhere. And but although this variety is different, but if you somehow by using if you use the localization theorem in equivalent cohomology, maybe I should write. Let me see. Maybe I think I will. Yeah. So anyway, so these two varieties are different, but there's some relation between them. That in that way you can explain the R matrix, existence of R matrix and the existence of poles of these R matrices. Let me see. So first, so this T. Let me see. I think. Then you can show that this T so first you must introduce some more notation. So G prime is a GL gamma of W1 tensor. So this acts on the product. And also acts on the variety T. And the first proposition is that this H star of G prime of T this is isomorphic to tensor product of this. And on here, so on the left-hand side, you have an action of, this is a representation of this H star of G prime of Z double. And this is a representation of, as I mentioned by Balagnolo, this is H prime, the representation of G double 1. So the existence of this isomorphism means that you have you can expect there is some relation between the homomorphism from here to here. So this is a first hint why this co-multiplication is something to do with this tensor product variety. The technical problem which we had in 2001 is that this isomorphism is not unique, not canonical. Yeah, but this point is a little bit technical, and as I mentioned, this technical problem is resolved by recent work of Morik and Kunkov. So I must mention, but this is a little bit technical, so I don't want to go so much in detail. But this isomorphism is not a priori canonical. So that is the one reason why our previous approach fails. But this becomes this was not a priori before, but now this Morik and Kunkov make this canonical. I think it's a little bit.
How do we get a representation of?
So but this is beer this. So this is the inclusion. In fact, this is a closed embedding. I should say that in the beginning. So this ZW has a natural representation by construction. So since this is a fiber product, so this I should write in here. So this naturally acts on H star of G of MW by convolution product. So you have some cohomology class in here, and you have a homology class in here, one copy. Then you pull back to the product, and then take intersection, and then push forward to another factor. So this, by construction, this is a representation. Of this AW. But the same definition works for T of W1, W2 instead of MW. Yeah, in fact, so this is a really general construction. If you have some for another extremal case that so in M0W you have some distinguished point which I usually denote by 0, And this I consider the LW, which is inverse of this 0 as a subvariety. Then this H star of G of LW is also representation of of this AW. And if once you have more generally, if you have M0, so you take some locally close subvariety in M0W, and if you consider this pi inverse homology of H star of G of pi inverse of S, then this is a again representation with AW. And M0 I will explain soon that TW1, W2 is of this form. So it's inverse image of. Are you still puzzled?
Yeah.
Let me see. So this diagram is really fundamental. And as I said, star can be pushed to Uhlenbeck space. So M0 of W, you can define T0 of W1, W2 in a similar way. So to define this, I really need to recall the definition of Boolean space. So I don't want to do today. But anyway, so you have this kind of map.
I mean, to construct that, you use the universal objects of the moduli space. But does the Uhlenbeck space have a universal?
No, this is not this is not modular space. That is one problem to act. I mean, to work working this space directly is really difficult because this is not. I mean, this is first of all singular, and this is not to find modular space of some object. Maybe you consider this as a modular space of some object in derived category, but I'm not quite sure you can work in that way. Anyway, so I denote this map iota and this map P. So by the way, so I mentioned that this kind of diagram appears in many other places also, but in fact this appears in the definition of the algebraic structure on the definition of the so-called linear whole algebra. So linear whole algebra is something by counting this kind of extension, you can construct some algebra, And in my setting, I use this existence of exact sequence in opposite way. Instead of constructing multiplication, I use the diagram in the opposite way to define a co-multiplication. So let me make a little bit more precise. So I consider that the derived category of constructible sheaves on M0 of W. So this is derived category G equivalent constructible sheaves on M0W with respect to some very natural stratification on M0. Then this AW H star of G of GW can be realized in terms of this language. So this is equal to X algebra in this category D of the push forward of the structure sheaf, constant sheaf on this MW with itself. So this is some general theory developed by Ginsburg. So once you have consider the cohomology of this kind of fiber product, then this pi. So you can understand in terms of constructible sheaves on this singular space. So now I use this diagram to define the co-multiplication. If we do this. So this is the first attempt which so I now make this more precise. So I use this diagram. So pi shrink of C of MW1 exterior product of no. I use in opposite way. So this is some constructive sheaves on here. Then I pull back by iota and then take push forward by P. So this is a constructible sheaf on here. And the proposition. So this is, so I should write MW here. And I should write T of W1, W2 here. So this is map. And I have a map into MW1 times MW2. And I have mapping here. But in fact, there is some technical point in here that in fact I'm a little bit cheating. In fact, so there is not. In fact, this is not really correct, and in fact, this is not really defined in general. In fact, actually you have the map M, which I denote by M0L of W1, W2, which there is some finite morphism. So in some sense, this is very close, but So in fact, you don't have this map, but instead you have this morphism. So first I write the result, which is A push forward of this pi shrink of C of M W1 exterior product of. And since AW is an extra algebra of this push forward, so this isomorphism induce a homomorphism from AW to A this induce. Almost. Because this is a functor, so you have some homomorphism in here. Then you have a homomorphism in here. But the problem is this is not really genuine homomorphism. So this A hat, which is almost isomorphism since this is a finite morphism. But so this is not really isomorphism in general. So I can't really have time to explain how to fix this problem to define the algebraic homomorphism in this setting. But how should I say?
What was the L again? What was the L?
A. L stands for Levy subgroup, and this I think I really need to mention what is really this variety is. So Uhlenbeck space is the pair of this is the disjoint union of pair of locally free sheaves of smaller chunkless times singularities. It's Sn of C2 divided by gamma minus origin and some scrapership at the origin. And this M0 of LVW is W1, W2 is not the product of Uhlenbeck space. Instead, you only have one copy of singularities. This is M0 of locally free of V1 W1 times V1 prime and M0 of locally free V2 prime of W times just one copy of singularities. So the map, yeah, in the rank 1 case, if both W1 and W2 are isomorphic, are rank 1, then this is the product of symmetric here. But here you have addition map. To map n plus m symmetric powers of C2 divided by gamma. So this A is some analog of this map. I'm sorry, so I already over time, so I stop here.
Are there any questions?
So does your R matrix indeed intertwine coproduct?
R matrix intertwined coproduct is defined by using localization theorem in equivalent cohomology. So once you tensored with the function field of the equivalent cohomology of a point, then equivalent cohomology of T of W1 then both are isomorphic to equivalent cohomology of a fixed point. In this case, there is a natural cyst action acting on fiber of extensions. Then this fixed point set is just product of MW1 cross MW2. So the fixed point set is the same for TW1W2 and TW2W1. So that's why. So once you tensor with function field, two modules are isomorphic. That is our matrix.
So it's saying the C star fixed extension split. Is that what? Is it that the C star
C star acts on five.
split of the here?
C star fixed point means this extension split. So the C star acts on, so this is the total space of extensions, and the C star acts on multiplication of fibers, and the fixed point just means the extension split.
That space is smooth or something? That T space is smooth?
T is not smooth. T is singular. For example, what is the simple example? In some cases, it's like so on the so when MW is the minimal resolution of simple singularities, then the TW1 W2 is some subvariety. So this is something like this. So you have a chain of P1s, and you have some copy. This is a strict transform of the axis. So T is like this variety. And if you change the load of W1, W2, then instead of x-axis, you choose y-axis. So this is an example of T variety.
So confused by something because to motivate this was that this extension is sort of non-commutative, right? That you made the order, but when we went to when you use localization to go to the fixed points, then they're all split. So then it seems like it should then be commutative. So
this is the same. So this is the same. So once so the R matrix is a function in variable u, which corresponds to the equivalent parameter for the group action. And I mentioned that this R matrix interchanges V tensor W and W tensor B, but it has some pole when you specialize U to some special point. That means we need to tensor with this function field. So this isomorphism is not defined without extending the scalars. So this is a generic point in the parameter space. So this structure is compatible with this algebraic structure.
Are you happy?
Is it the same story for quantizing developing algebra and for Yangian, or is there
Well, there's one technical problem. This kind of sheaf theoretic approach works only on homology, not on the K theory. So I don't know how to deal with Yang. So this story works for Yangian, but so far I don't know how to do with quantum affine algebra.
Any more questions? Well, shall we? I don't know if you do this.